So, we continue with our discussion on problems in mass transfer. We are talking about problems concerning steady state and unsteady state diffusion. However, before I take up the next problem, I would like to make a small correction as far as the previous lecture is concerned. And you remember I was talking about calculating the rate of permeation, that is the first steady state problem in diffusion, and that I think I mistakenly said that it is the diffusion of hydrogen through platinum foil, but it is not so. It is actually diffusion of hydrogen through a nickel foil, because the data, diffusion data etc., which I have presented was actually for diffusion of hydrogen through nickel and not diffusion of hydrogen through platinum. So, that needs to be noted, and accordingly I have written, though I have not given you the explicit value, I wrote rho platinum to be density of solid platinum to be included in the final expression for conversion of the Sievert's law constant. So, therefore, this is wrong, and there actually rho nickel, which is equal to, and this value needs to be substituted, which is in gram per cc. Okay. So, please make a note of that, and if you substitute this value, the answer to the problem, as I have quoted, is 1.7 into 10 to the power minus 12. It is not so. The answer of the problem is rate of permeation will come out to be according to my calculation. So, you may verify these numbers, minus 10 gram mole per second. That is the rate of permeation. So, instead of the value, that final value that I have written without substituting the value of this parameter, which should not have been done. So, if you substitute in the expression rho nickel is equal to 8.9 grams per second, that is the final answer you should be getting. You may check yourself with respect to whatever I have discussed in the last lecture. So, now let me complete the discussion on the penetration length, and if you remember that I was talking about penetration length at 900 vis-a-vis penetration length at 1300. These are at degree centigrade, and I have shown that these values are going to be exponential, minus 142,000 divided by 8.314, that is the value of R, and this is 1173, and divided by exponential. So, that is, I just want to give you the final values if you do the calculation and make one or two deductions on the basis of the value, and then 8.314 multiplied by, for corresponding to 1300 it is 1573, and the whole thing is raised to the power half, because you remember that the penetration distance is equal to 4 times of square root of d into t, and that is the square root comes, t and t cancels out. And if you do that, then you find out that this is equal to e to the power minus 14 point, let me see my notes. Okay. This value comes out to be 14.56, yes, and this value comes out to be e to the power minus 10.85, and that is raised to the power of half. And if you use your calculator, you find out that this value is going to be equal to 0.156. Therefore, we can say that the penetration depth at 1300 degree centigrade is inverse of this value, comes out to be 6.39, or roughly about 6.4 times penetration distance of 900 degree. That is the value. So, we have increased the temperature from 900 to 1300. So, if you take that ratio, we find out that it is 1573 by 1173, and that is roughly is equal to 1.36, okay. So, or 1.34. So, by merely increasing the temperature 1.34 times, we can see that the penetration depth increases by a factor of 6.4 or 6.4 times it increases, and this is because of the fact that diffusion is a thermally activated process, and the characteristics of the thermally activated process is an exponential dependence, and it is because of that exponential dependence we have such a large increase in the value of the penetration distance. Now, this is with respect to the problem. So, you could, one can give you, for example, ask you that the reverse way, the same problem can be posed. For example, the ratio is given and you may be asked to calculate that by what factor the temperature needs to be increased, and so you have to go in the reverse direction, okay, and get yet the same answer. So, either the temperatures will be given, you will be asked to calculate the ratio of the penetration depth or the increase in the penetration depth or decrease in the penetration, change in the penetration depth, or alternatively you may be given the penetration depth and you may be asked to find out that by what factor or by what amount you have to change the temperature. Okay? The problem can be posed in either of the two ways. Now, I want to show you the steady state, unsteady state diffusion in a slab geometry, and directly show you, the resemblance between a heat conduction phenomena in a slab vis-a-vis mass diffusion in a slab. So, we pose the problem unsteady state, unsteady 1D diffusion, one dimensional diffusion in slab geometry. Obviously, the properties are all constant. Okay? So, we set the problem like this. This is the slab, this is the line of symmetry. The slab is a length of 2L. This is y is equal to 0. This is L plus L and this is minus L. If you recall, I have set the same problem for heat conduction also. Okay? So, this is the boundary of the slab. And there is an initial concentration here, okay, because it is an unsteady diffusion. So, the initial field is to be given, and let the initial field be given as, say, concentration of the species I, that is diffusing through the solid. So, this is a solid through which a solute is diffusing, and that is the species I. So, C I at 0 is equal to, suppose I give you a value is 0.05 with percentage. Then the surface concentration akin to a constant fixed surface temperature C of I at S is equal to 1 wet percentage. So, mathematical description of the problem is like rho Cp, this is the heat transfer equation, and I will write the corresponding K, this is y square, and in this particular case we will have, it is concentration of I and diffusion coefficient, and this is. So, there is a one-to-one similarity, as you can see, okay, and I have indicated that if you write this equation like this instead of K as alpha, because properties are all constant in which alpha is thermal diffusivity. So, the moment you substitute alpha by D, the value of T can be interpreted as the value of Ci. There is one-to-one correspondence between the two set of equations. Okay? And you remember, I have non-dimensionalized the equation and given you the solution. Okay? So, and we remember also that for an unsteady state in slab geometry, the solution will always come out to be in the form of an infinite series. For a semi-infinite geometry, it is in the form of an error function. So, this is the value. The initial concentration is given to us, surface concentration is given to us, The diffusion coefficient value is, let me see what is the value that I have used. I think it is something raised to the power 8 minus 8 or so. So, 4 into 10 to the power minus 8, 4 into 10 to the power minus 8 meter square per second. That is the diffusion coefficient, diffusion of I through the medium. Okay? And I want to calculate at time t is equal to 10 to the power 5 seconds. And this 2L is nothing but, we can say that it is L is 0.1. So, this is so 0.2 meter. Okay? So, which essentially means that L is equal to 10 to the power 1 meter or 0.1 meter, that is what it is. So, these values are given and I want to calculate that at the center of the slab, what is the concentration C, and I say C of I, and this is at center. Okay. So, therefore, I will say y is equal to 0 and t is equal to 10 to the power 5 seconds. So, we can, for this I have shown that infinite series solution. So, for this also we can write the infinite series solution, and that solution can be given in terms of theta, a dimensionless concentration, which is a function of dimensionless distance and dimensionless time, and as per our previous definition, this can be written in terms of, say, C of surface minus C and C of surface minus C of 0. I am just dropping the suffix I. Okay? So, whatever concentration I write, it is with respect to the diffusing species I, that should be understood. So, therefore, the same boundary conditions apply, that at initial boundary condition theta is equal to 1, as you can see, Cs minus C0 divided by Cs minus C0, this is 1. When boundary condition is Cs minus C0, Cs, which is 0. So, therefore, so dimensionless boundary conditions are, here it is going to be is equal to 0 and the initial corresponding initial condition is going to be 1. Okay? So, these are in terms of dimensional boundary conditions, initial condition and surface condition. This is surface boundary condition and this is initial boundary condition. I am deliberately mentioning the theory, not just writing the formula, so that it gives you better understanding of solution of the problem, because I cannot solve too many problems while trying to increase your capability of solving or handling of problems. So, not every type of problem it is possible to discuss through such lectures. So, therefore, the underlying theory is given some emphasis, a little bit of emphasis, so that this allows you to maneuver various calculations that you may come across while solving problems of interest. So, therefore, in this particular case we will say that this is equal to, as far as the infinite series solution is 2 times summation n is equal to 0 to n is equal to infinity, as an infinite series solution minus 1 raised to the power n plus half into pi, and then we have 2 different terms. First term is the exponential solution, exponential term, and that is minus with respect to the time. So, the product solution technique, okay, pi square tau, and this is equal to cosine of n plus half into pi eta, where tau is equal to dt by L square and eta is equal to y by L. That is what it is. That is the definition. So, either I can write in terms of dimensionless concentration. Now, if you look at the value of dt by L square, which we call as a mass Fourier number, Fourier mass, then we put diffusion coefficient, which is 4 into 10 to the power minus 8, time, which is 10 to the power 5, and L square, which is 10 to the power minus 1 square, and this value will come out to be something like 0.4. And if you recall my lecture on heat transfer, okay, when the Fourier number, mass or heat Fourier number will be greater than 0.2, in that case what happens? The large time solution applies, which essentially means the large time solution means that only first term of the infinite series is meaningful. So, therefore, we can say that according to this scheme we can write that this is equal to 2 by pi into 2 exponential minus pi square tau by 4 into cosine of pi by 2 into eta. Because we want to find out temperature at the center, okay. So, therefore, we can say that now we can change the values. So, we can say that theta is equal to theta as a function of eta, and eta is equal to 0, and this is equal to 10 to the power tau is equal to, as you have seen, 0.4, and then we can find out, we can write down that this is nothing but 2 divided by pi, okay, and then we have 2 exponential minus pi square into 0.4 divided by 4, and that when you put eta is equal to 0, that becomes is equal to cosine of 0 is 1, and this is the value, and this value comes out to be 0.475. So, we can go back to the definition of theta, okay. So, therefore, we can say that Cs minus Cc, where Cc represents the center point concentration, is equal to Cs minus C0, and therefore, we can say that Cc, the concentration, is equal to Cs minus C0 multiplied by 0.475, okay, and this is, if we take it here, then we can say minus plus Cs, and that is what we get, that. So, this is equal to 1 wet percentage, okay. So, CSC will be in the same unit, wet percentage unit 1, and then minus, we can say that this is equal to 0.95 multiplied by 0.475, and the answer comes out to be 0.55, and this is going to be in terms of percentage. So, we can handle steady state, unsteady state diffusion problems in Cartesian coordinate, either in semi-infinite geometry or in finite slab geometry, through the infinite series solution or through the error function solutions, and handle a wide spectrum of problems that we may encounter at the undergraduate level. Okay. Now, we will move on to our next topic, and so having discussed solid state diffusion phenomena and the problems, underlying problems, mathematical problems, we will talk about now a solid liquid mass transfer. Solid liquid mass transfer. So, if you consider briefly the theory, it says that if you have a solid which is this is encountered for example, in alloy dissolution in leaching processes, where there is interaction between solid and liquid, and the solid progressively gets dissolved into the liquid. So, bauxite leaching, ferroalloy dissolution, all these kinds of things you will see under this category. So, the mass loss, the governing equation here, the mass balance equation, the rate of mass loss from the alloy is equal to mass transfer coefficient times the area through which, and then we have the concentration gradient, where this is this. So, if you have a spherical addition, we can say area of the sphere, mass of the sphere. So, if you add a sphere and the rate at which the sphere is dissolving, its diameter is reducing or the mass is decreasing, is equal to mass transfer coefficient times the interfacial area multiplied by the concentration. This is the surface concentration and this is the bulk concentration. And this surface concentration, you must read the associated theory before you attempt these problems, okay, or try to understand or go through these lectures. Underlying theory must first be understood. And this is the equilibrium surface concentration. Why it is equilibrium, that is discussed in lectures or it is found in textbooks, because the dissolution, chemical reaction associated with the dissolution is considered to be at equilibrium, and this is basically we consider that the transport through the boundary layer is rate limiting. The bulk concentration is exactly equal to the concentration at the edge of the boundary layer under the assumptions. So, therefore, this is known from thermodynamics. This is the solubility limit. So, this value will be known, and this value Cb, because as the solid is dissolving, the bulk concentration is progressively going to increase, but the bulk is typically so large. Okay? So, therefore, as a first approximation, we can consider this to be equal to 0. If it is not 0, in that case what happens is you will have to consider an additional equation, because from you have only one equation and you can only get one unknown. But if you also treat this Cb to be unknown, in that case a second equation needs to be brought in, where from you can solve two equations to get the values of the two unknowns. So, if you now consider or apply this equation to a spherical shape addition, to a sphere, and then this equation is cast in terms of the rate of change of radius of the sphere Rs is equal to Km, the mass transfer coefficient, times Cs star divided by rho star, where rho represents, because in the mass term, if you remember, mass of the sphere is going to be volume times the density, and that is how the density manifests here. So, therefore, it is understood that if mass transfer coefficient, because as I said, this is going to be known to us from thermodynamics, rho s will be known to us. If mass transfer coefficient is given to us, then the rate at which the radius is decreasing can be found out, and on the basis of that we can determine that what is the complete dissolution time of a solid. Okay? Now, there are two possibilities here. Either Km, if you take it to be only a function of initial radius of the sphere, Rs of the sphere, okay, which is initial, then Km is constant. So, the rate is going to be equal to constant. You will get R versus T, a linear line. On the other hand, if you say that Km is a function of instantaneous radius, in that case this is a function of Rs. So, this becomes a non-linear equation now, okay, and therefore, you will see that the variation of radius with time is no more going to be linear. So, there are two possibilities, two way problems can be cast. Okay. Now, where from Km comes? The Km comes from a mass transfer correlation, solid liquid mass transfer correlation, and for laminar flow, if you consider that the flow around the solid, because in dissolution and leaching problems always there is going to be stirring. We know that from theory, higher is the stirring, more is the mass transfer coefficient, and more will be the rate of dissolution. At very fast rate, the radius is going to be decreasing. So, let us see that, let us assume Km is constant, and it is based on initial radius of the sphere, initial diameter of the sphere. That is a given condition. And let us now set a problem to find out a complete dissolution time. Okay? And the problem is, so we have a sphere of molybdenum sphere. So, I am proposing the problem formulation, and this, the diameter of the molybdenum sphere is 70 mm, The solubility C A star value is given to be 4542 at 95 kg per meter cube, kg of molybdenum per meter cube of steel at 1600 degree centigrade. The density of molybdenum, very heavy element, it is 10,000 kg per meter cube. Mu of steel is given to be 0.007 kg per meter second. Density of steel, raw steel, is given to be 7,000 kg per meter cube. Schmidt number is given to be 300. Velocity past the sphere is given to be 10 centimeter per second. And we have to consider, as a first approximation, we consider that the flow around the sphere is laminar and the mass transfer coefficient is governed, dictated by the popular initial diameter based DSI, okay? Reynolds number raised to the power half and Schmidt number raised to the power 1/3. The popular Range-Marshall correlation. And the task is calculate complete dissolution time. It is not melting, it is dissolution, because molybdenum does not melt in steel. Molybdenum has a greater melting point than the steel operating temperature, which is at 1600 degree centigrade. So, all these properties which are given here corresponds to 1600 degree centigrade of steel. Dissolution of molybdenum sphere in a stirred steel bath, that is the problem, and we want to calculate the complete dissolution time of the sphere. So, let us now calculate the Sherwood's number. So, if you calculate the Sherwood's number, we have to calculate the Reynolds number, okay? And the Reynolds number in this particular case will come out to be almost 7,000 raised to the power half, okay? And Schmidt number is given, which is 300 raised to the power 1/3, and if you do this value, then you will find out that Reynolds number raised to the power, this will come out to be 83.6, and this will come out to be 6.7, okay? And therefore, you will find out that the Sherwood's number value, diameter based, initial diameter based DSI is going to be 2 plus 0.6 multiplied by this, and this is going to come out to be something like 337.8. And what is the definition of Sherwood's number? Sherwood's number is the mass transfer coefficient into diameter of the sphere, initial diameter of the sphere, divided by diffusivity of molybdenum in steel, or you can say molybdenum Fe. That is what is, and therefore, this is equal to 337.7. So, we can now substitute the values. So, if you have, so the value of Km, which will come out to be, is, if you substitute the value of Km multiplied by the initial diameter of the sphere, which is 70 into 10 to the power minus 3, and diffusion coefficient, from this table we can see that the diffusivity is given, and that diffusion coefficient is CSU, okay, Smith number, and let me see what is the diffusion coefficient. So, diffusion is equal to, that data should have been given here, diffusion of molybdenum into Fe, and that is given to be 3.2 into 10 to the power minus 9 meters square per second, that is also given. So, 3.2 into 10 to the power minus 9, and that is going to be equal to 337.7, which gives us mass transfer coefficient is equal to 1.54 into 10 to the power minus 5, and mass transfer coefficient has the unit of velocity meters per second. Now, if you do this, substitute here, so you get 1.54 into 10 to the power minus 5, okay, and then this is going to be equal to C S star. So, this is going to be basically divided by 10,000. So, it is going to be 0.4542, or we can take it to be 43. Okay, that is the value, and this is going to be meters per second. That is what is the dimension of this term, and this is going to be 0.70 multiplied by 10 to the power minus 5 meters per second. So, it is now a piece of cake to find out that what is the complete dissolution time, and that complete dissolution time can be very easily calculated, because we know that what is the initial radius. So, we can say that this is going to be equal to 0 minus 0.035, okay, or we can say, so minus 35 into 10 raised to the power minus 3, that is what it is, divided by 0.70 into 10 to the power minus 5, and that is equal to T sub resolution. So, we can say that this is 5, and this is, we can say this is 10 to the power minus 7 into 10 to the power minus 6. So, 5 into 5,000 seconds. So, that is what is the answer to the problem. So, this is the mass transfer coefficient, the moment we have calculated. So, radius is, this is found out to be rate at which radius is decreasing, and then this is 0 minus the initial radius, final radius 0 minus the initial radius. So, R I, and then this is equal to T dissolution, that is the integral. Okay. If you integrate it, and this is 0.7 into 10 to the power minus 5, and therefore, R I is 35 millimeter. So, because diameter was taken to be, diameter of the sphere is taken to be 70 mm, if you remember, I think I have erased it. So, CS through S, okay. So, diameter d sub S is equal to 70 mm. Velocity molybdenum is the diameter, yes. Diameter of molybdenum sphere, that is what it is. Several hours, 2-3 hours time is going to be. So, seconds, so if you divide by 3600, you get hours. So, it is going to be between 1 and 2 hours, that is the time, because dissolution is an extremely slow process. Now, the same problem I have solved it in a very easy way, okay? And I have assumed that mass transfer coefficient is a function of initial diameter only. So, it's constant basically. So, this has also indicated that we can approximate this in terms of the mass transfer coefficient as 2 is redundant. So, therefore, we can say that this is Reynolds raised to the power half into Schmidt raised to the power half. So, this is actually beta times, and this is going to be radius of the sphere, okay, raised to the power half. And similarly, if you see here, so therefore, you can find out that the mass transfer coefficient in that case is going to be beta prime, and here is going to be diffusion, here is going to be diameter or the radius, and this is going to be radius of the sphere raised to the power minus half. So, therefore, if the mass transfer coefficient is to be treated as a function of diameter and you would be asked to calculate the resultant complete dissolution time, in that case from the correlation these approximations are to be applied, that the factor of 2 can be ignored because this component is 335, this is 2, and that is how 337 has come, and then the moment you do it, life becomes simple and you can find out a relationship between Km and Rs, and now you can integrate this, and this is going to be now the final expression will come out to be minus. So, you will have Rs, and then we will say Rs raised to the power half minus half, and then this is going to be whatever is the value here, some constant will come that you will have to calculate, okay, beta double prime, and this is going to be dt. So, that is the integration that you have to do. So, Km is to be substituted. So, this factor is going to, you have substituted beta. So, this beta prime is essentially beta prime multiplied by 0.45, and what is that value? 45429. So, 4543, that is what is the value. So, and you have to integrate this from R is equal to Rs is equal to initial diameter Rsi, and that is the final diameter, and then you can say that we can integrate this from at time t is equal to R is equal to this time, and this is t is equal to t solution. So, that is the final. You can do this, get the value, and you can compare with our value of simplified estimation of 5000 seconds, and then see that considering whether it is justified to take it, how different the results are, whether you consider, if you consider a constant radius vis-a-vis a time dependent radius for the estimation of mass transfer coefficient. The last kind of problem that one encounters, or one solves in classes, undergraduate classes, is very simple problems dealing with two fluid mass transfer under laminar flow, and I want to just show you one particular example and then conclude my discussion on mass transfer. Okay. So, problems on two fluid mass transfer. Again, I suggest that you please read the theory and then you try to solve the problem, two fluid mass transfer. The theory of mass transfer really does not change much. The whole artifacts of the procedure that one considers is a different approach for calculation of the mass transfer coefficient. So, the moment you calculate the mass transfer coefficient multiplied by area multiplied by the concentration difference will give you the rate of transport, and by knowing the area you can calculate the rate of the transport. So, in the two fluid mass transfer cases, those correlations are not applicable. Sherrid's number is equal to whatever I have shown, they are the correlations for convective mass transfer between a solid and a liquid, but when you have two fluid you have different kinds of correlations which come there. Now, typically you have mass transfer coefficient is calculated, has an expression which is given in terms of d divided by pi t. How this expression is arrived at, I think that is discussed extensively in lectures concerning two fluid mass transfer at the undergraduate level, and this is the result of the Higby's penetration theory or Higby's model. Since diffusion coefficient is known, the whole task of calculating the mass transfer coefficient boils down to the estimation of Te, which is known as the exposure time. The moment you can calculate the exposure time, then you should be able to calculate the mass transfer coefficient very easily. This exposure time, for example, suppose two fluid mass transfer case, suppose a bubble is rising through a liquid with a velocity of ub. If the diameter of the bubble is dB, okay, then the exposure time is given in terms of dB by u sub b. Diameter of the bubble in centimeter, ub in centimeter per second, so Te is equal to. Similarly, if there is a surface on which is moving, for example, okay, with a certain velocity, say v surface, in this case the exposure time basically is given in terms of the distance, which is the radial distance, divided by the surface velocity, that is the exposure time. So, these are simple cases of bubbles rising through a liquid or a spherical cap bubbles rising through a liquid. So, if a bubble is spherical cap, in that case it is only this distance that needs to be considered in the estimation of exposure time. So, let us now pose a problem. So, let us accept this definition and then see that how can we apply solve a problem involving two fluid mass transfer. Let me propose that suppose formulate a problem formulation. Suppose we have a melt which is contained in a vessel and which is being stirred, okay, where the flow pattern goes something like this. Okay. The surface velocity is given to us. This is the radius of the vessel and this is surface velocity. This may be experimentally determined, rough. So, estimation. So, these are all approximate estimation, but they works very good for first hand estimation or the kind of problems that we solve. So, now suppose this melt typically in industries, for example, for spheroidizing. So, you have an iron carbon melt and you tend to add magnesium, which spheroidizes carbon, but the magnesium gets evaporated. So, there is a loss of magnesium. Okay. So, we want to find out that as a function of time, as the processing goes on, how does magnesium, and suppose if the magnesium falls below a threshold level, the spheroidizing action is not complete. So, we want to find out a critical time by which the magnesium concentration in the bath has fallen to 50% of the initial concentration. Now, so the magnesium basically, okay, it goes to the interface, and at interface the magnesium which is in the dissolved state, okay, it becomes magnesium gas, and that is how it goes. So, the moment dissolved magnesium reaches here, it escapes. So, the rate at which, so we assume that the rate of magnesium transport to the surface is controlled by the melt phase mass transfer phenomena. So, this is the chemical reaction that is known to us, and the moment this rate of the chemical reaction is very fast at high temperature. So, we can assume that the magnesium concentration at the surface is approximately 0, because whatever magnesium is going to reach to the surface, because this reaction is very fast under the assumption that melt phase mass transfer is controlled. So, this is equal to 0, and we have a magnesium bulk which is changing as a function of time. It is because of this escape of magnesium. So, the task is that we will give you the initial magnesium concentration. So, magnesium initial in the bath is given. We will give you the diffusion coefficient of magnesium in the melt. We will calculate, we will give the vessel dimension L and R, and we would like to calculate the time at which we will say that the concentration in the bath magnesium bulk has become 0.5 times of magnesium initial. That is the, give me the time, calculate the time by which this condition is valid in the system. So, now we go on to solve the problem. So, what are the values that we want to give you? So, we want to give you a value of L is equal to 3 meter, this is equal to 1.5 meter, diffusion coefficient is equal to 3 into 10 to the power minus 9 meter square per second, because we want to have a ratio. So, this is redundant, actually not needed, as I will show later on. Okay. So, therefore, if you do this, we can find out that the exposure time here is equal to R divided by the UV or U surface, and the surface velocity is also given. Surface velocity from measurement is given to be 50 centimeters per second. So, R is equal to 1.5 and this is equal to 0.5. So, therefore, this is equal to exposure time is equal to 3 seconds. Okay. So, therefore, mass transfer coefficient is 2 into diffusion coefficient, that is 3 into 10 to the power minus 9, this is 3 multiplied by 3.142, and this value comes out to be 3.64 into 10 to the power minus 4. Now comes establishing the mass balance equation. The mass balance equation goes like this in the system, that the rate at which, if V represents the volume of liquid in the system and this is bulk concentration which is changing, net rate of decrease of magnesium, in case this is we will have volume. So, this is kg per meter cube if it is, then meter cube cancels, this is actually the mass flow rate term. The rate at which magnesium is getting lost from the system is exactly equal to the magnesium which is, and the driving force here is C magnesium bulk minus C magnesium surface, and this term is going to be taken to be equal to 0. That is, so therefore, since A by V is equal to, so V is equal to pi r square L and this is equal to pi r square. So, this we can say this is equal to this. So, Km by L is actually the rate constant, okay, because meter will cancel, this is a dimension of 1 by second and that is what is going to be. So, this is the first order mass transfer process, and then we can say that dCmg bulk by Cmg concentration, okay, bulk, and that is equal to minus Km by L. And this is subject to the condition that at T is equal to 0, we have Cmn bulk is equal to Cmn initial. So, therefore, we can now say that if you integrate this, then what happens is that we have ln Cmg bulk is equal to minus Km by L T plus C1, and this C1 when t is equal to 0. So, this is equal to ln C Mn Mg initial. So, therefore, we can say that if we now, therefore, we can say that it is C magnesium bulk by C magnesium initial, okay, is equal to minus Km by L into, so and this is equal to minus Km mass transfer coefficient by L into T. And this value is given to be C magnesium bulk is 50% of this. So, this is actually ln of 0.5, that is what it is. And the mass transfer coefficient we have calculated to be is equal to 3.64 into 10 to the power minus 4, and then we have calculated, we know the value of L, which is 3 meters, and this is equal to T, and therefore, the only unknown T can be calculated and found to be something like 5827 seconds or 1.6 hours. You can solve, this is basically applicable to laminar flow systems. So, using the Higgins penetration model, you can find out, for example, bubble to liquid mass transfer. If you assume a droplet, okay, a liquid droplet settling or rising, you can also find the corresponding mass transfer rates, corresponding extraction rates. All these kinds of problems you should be able to solve, and as I said, that the crux of the problem is to calculate that what is the exposure time. Having calculated the exposure time, calculate the mass transfer coefficient, and once you have established the mass transfer coefficient, establish the governing mass balance equation, okay, and then plug in the values to get the answers. So, we have sort of discussed all the problems that we can anticipate at undergraduate level in on mass transfer. We will discuss now some problems associated with fluid dynamics, Bernoulli equation, etc., to wind up our discussion on this segment of online instructions.